Hello, friends! Welcome back to day 2 of the Regression Challenge. So hopefully you all had a good time yesterday and you learned a lot and it wasn't, too intimidating. Today we are going to be learning about residuals and we're going to be making diagnostic plots. So you will have gotten an email with the link to the challenge, which is just Regression Challenge Day 2 from me, and my username is rtatman. And two things. So the first is that we're going to actually be writing our own functions today. We're not going to be writing our own functions. Sorry, that was absolutely a lie. We're going to be fitting our own models today. So we need to be familiar with R's formula notation. So the general idea is that the output, the thing you're trying to predict, is on the left. Sorry, I did have to look at my hands there. And what you are using to predict it is put on the right. And we're going to work today with single inputs, but in the future we're going to work with multiple inputs, and that will be not tomorrow but Thursday. We're going to work with multiple inputs to predict an output. The other thing that we're going to do today is we're going to talk about residuals. So I can actually show you what this is. Oh, and this is somebody's notebook from yesterday. This is Daoshang's notebook, so I'm using it. Sorry if hopefully you're not embarrassed. It's a very nice notebook. And what Dao was predicting was, given a temperature, how many bicyclists will cross the Brooklyn Bridge? So the residuals of this model are the differences between our predicted value, which is on the regression line, and the observed value, which is the point, for a given input. So each point will have a residual, each observation will have a residual. And what we're looking for today is we're making sure there's no patterns in our residuals, and I'll get to that in a little second. But the thing to keep in mind with residuals, which I was mistaken about last year, is that the residual is actually the error. So it's this way. It's how far off our actual model is given a specific point on the axis that we're making our prediction on. It doesn't go this way diagonally to the nearest point on the line, because we don't want to we want to know how far we are off for a thing that we actually observed, not for sort of the hypothetical version where actually the temperature is different than the one we actually observed, if that makes sense. So that's the idea. And we're going to use... I thought I'd made it so that this input wouldn't show, but I guess I didn't. Oh, I haven't forked it. Oh, sorry, it's been a very long day for me. So we have, it's thinking to itself. So we have two libraries we're going to be using. We're going to be using the tidyverse library again, and that lets us do things like use tibbles, which are a special type of data frame, and also use ggplot. And we're also going to be using this boot library that will let us do diagnostic plots for GLM models, so generalized linear models, which are different. Hide output. So when this bit of the cell says that when you compile the notebook, so when you hit publish, I don't want to see the output because you don't need to know all that nonsense. That's not interesting or important. And the boot library for doing diagnostic plots for generalized linear models, not general linear models. Those are different. I know. Who lets statisticians name things? And then we're going to read in two data sets, and these are both data sets that are surveys of technical professionals. So this survey was just released by us, Kaggle, and it's about machine learning professionals and data scientists. And this is the Stack Overflow developer survey from 2017. So that's a survey of a lot of software developers. And I'm going to be working with the Kaggle dataset, and y'all are going to be working with the Stack Overflow dataset. And I'm just going to do a little bit of cleaning, so I want to make sure that I only get rows where I know compensation amount and where it is larger than 0. And I also want to remove commas or periods, because sometimes people will write numbers, like really big numbers, like 1 million with commas in it, or sometimes they'll write 1 million with periods in it if they're particularly European. Yeah, so the reason we're cleaning this data in this way is that I'm interested in seeing if you can predict what someone's salary will be based on their age, because I have the intuition that older machine learning practitioners are probably going to be paid more because they're probably more experienced. So we will see if that's the case. So we're going to fit our model, and we're using this GLM function, generalized linear model. And we are going to give it the formula that I was talking about up there. So our output is cleaned compensation amount, which I got from cleaning the compensation and then assigning that to a new column in our data frame. That's what mutate does. It takes whatever is over here and then gives it a new name and adds it to your data. It adds it to your data frame. Oh, so I've actually mutated twice, and then the second time I am just replacing this column, making sure that it's numeric. So I have that cleaned compensation amount. I think that the important input is age. I want to say that I am using my specific data frame. This has compensation data frame. And I want to say that it is Poisson, because salary is a count value, right? You're usually paid in, round increments of whatever currency you're using. And it also isn't usually less than 0. If you're being paid less than 0 for your work, maybe try and find a new job. Maybe that's not a good job. All right, so we're going to train our model, and we're going to talk tomorrow. Oh, yeah, I better do all of these things before that, huh? And we're going to talk tomorrow a little bit about analyzing models and interpreting models, but it does not matter if your model is not good, right? You can do a lot of interpretation of a model that's deeply nonsensical, and, you'll get numbers out, but it won't mean anything, And that's what diagnostic plots help us do. They help us make sure that our model is actually what's the word I'm looking for? Reasonable, sensible, right? It tells us something about the world. So this function, diagnostic.plots, is from the boot package, and it's going to show us a number of plots. And before we get into these, I just want to tell you, these are all horrible. None of these should look like this. So this shows you the residuals versus the linear predictor. And the generalized linear model family is built under the assumption that your residuals should be normally distributed. So you shouldn't see patterns. It should be drawn sort of randomly from this distribution, if that makes sense. So the fact that I see a line here is awful. I don't want to see a line. I want to see sort of like a cloud. And the fact that I'm seeing outliers here that are really clear and easy to pick out is also very worrying. I should see sort of like a fuzzy cloud here. Here, what I want to see is a line that goes diagonally this way, and I want to see all my dots on the line. So this is sort of plotting the residuals. So this is the residual of the first. So if you take all the residuals and then sort them, this is the most negative residual, the second most negative, the third most negative, so on. The most positive, the second most positive, the third most positive. And you want those to be sort of on a straight line, and the farther the line is from straight, the least normally distributed your data is. So that's not a straight diagonal line. You can see there's some really strong outliers that are real messing us up. Here, you want to see a little cluster here in the bottom corner here. The Cook statistics and this, which is the, what's it called? Leverage, which is a measure of leverage, tells you how influential each individual point is. And you don't want any one point to be super, super influential. That's a warning sign. Those are some like weird outliers and you don't like them. So you want all your data to be down here, and these guys are making me worried. And then this is this same y-axis, the Cook statistic, but now it's just plotted across our data frame. So this is good for seeing if there's like some pattern in your data frame and your observations. So maybe they like go up over time and you're missing some sort of linear process that's happening underneath your data you don't know about. So that's what that plot tells you. All of these plots are telling you, no, bad model, do not use this model. And there's just sort of some narration here, so you can look back at that for your notes. So what I'm going to do is I am going to remove salaries of above 150,000, because I didn't normalize for currencies. So these salaries are all in a bunch of different currencies, and I bet like some of the weird outliers are due to being in yen or something that's much less, where the individual currency is much less valuable than others. So once I remove those and then train another model and then get my diagnostic plots, things look a lot better. So this is sort of like a cloud. There's a little bit of patterns in it. So you'll notice that there seems to be a floor, which makes sense because again, you should not be being paid less than 0. And there's sort of like also a floor in this direction. So there's some patterns, but there's not like a strong line like we saw earlier. That was really worrying. I'm fine with this. So they should make a diagonal line this way. And you can see there's a little bit of skew in the data. So it seems to be growing more sort of in the middle age range, but it's still more or less on a center line. I'm fairly happy with that. When we look at the Cook statistics versus leverage, I guess, you can see we still do have one fairly influential point. But if we compare it, so this is 1500 and this is 0.03, it is about 1/3 as much leverage and just orders of magnitude less influential. So it's still, maybe something to be worried about, but not at all on the same degree as these guys. And we can also see this if we sort of look over here. So we can see, because this range is lower, we see more of the noise in the bottom of the data here, and that's fine. And I'm a little bit worried about this point, but this model with the outliers removed is definitely much, much better than the previous model that we had. And no model's ever going to be perfect, and if it is, you should be worried. But this is a good way to sort of like, take the temperature, check the health, make sure there's nothing super weird going on. So, as a final step, let's go ahead and plot our data and fit our model to it. So if we see here, I'm going to zoom out a little bit so you can see. So this is age, this is compensation, and this is our fitted line. So we can see, yep, sure enough, as people get older, their compensation goes up. Oh, and something that some people brought up yesterday is, this is Poisson, and we fitted it using the Poisson family, and you can't see the error bar, and that's because if we make the size of the line 0, which will make the line disappear, you can see that the error bar, I'm going to zoom way in for y'all, is, scroll. It's in there, it's just very thin. There's a very thin error bar. So you can sort of like see it there. That's the error bar. All right, zoom out. Oh, I went too far. Anyway, so that is the second day of the challenge. You're going to fit a model, you're going to make some diagnostic plots, and I'm also not giving you a specific question to ask. I'm having you guys develop your own questions because that's something that you're going to end up doing a lot in any data science position. So I look forward to seeing you guys' work, and I will see you tomorrow. Bye-bye.